So continuing from where we have stopped, okay, we can consider here that we can take a special case of the what you call correlation coefficient will be plus or minus 1. Okay, so this will be the special case we'll examine. For doing this, we'll consider the x and y deterministic case in which we considered in 2.60. In the 2.60, we have the deterministic case of the y is equal to ax plus b, y is equal to ax plus b. That is what we will consider. So if y is equal to ax plus b, then the we can consider the correlation, the covariance of the x and y, which is given by the formula E of the covariance we have already written over here to be with respect to 3.38. So in place of y, we can write ax plus b, and in place of mu y, we can write a mu y minus b. That's the quantity which we will get. Okay, so if we take it that way, then we'll get x minus mu x, ax plus b because of y, and because of mu y, we'll get mu x, mu y, we'll get mu y is equal to minus a mu x minus b, and this b and this minus b will cancel, and from these two, ax and minus a mu x, you can take out a common, and this a can be totally taken out because it has nothing to do with the expectation. It is just a constant, and hence you'll get x minus mu x into x minus mu x equal to x minus mu x whole squared. And this expectation of x minus mu x whole squared is nothing but the variance or standard deviation squared. Okay, so covariance will be equal to a sigma x squared. Okay, also from 2.62, okay, the standard deviation will be 2.62 is what we call here. So 2.62 is sigma y squared is equal to a squared sigma x squared. Okay, this we are using there. So we will get from that sigma y is equal to plus or minus root of a squared sigma x. We had sigma y squared is equal to a squared sigma x squared, and that will lead us to sigma y is equal to this quantity. And if you substitute it within the correlation coefficient of xy, we will get the quantity which is like this. Okay, so that will give us the value equal to plus or minus 1. So what does that give? This will give us that the correlation coefficient is equal to plus or minus 1 if we consider that there is a deterministic relationship between x and y. Okay, if there is a deterministic relationship between x and y, then the correlation coefficient will be plus or minus 1. Okay, so now let us take some of the examples concerned with that. So let us take the figure 3.71a. So 3.71a is here. This is the 3.7a. Okay, so this one you can see over here. In the x direction, it is from 0 to 1. In the y direction, it is from 0 to 1. So the mean will be half here, the mean will be half here, average of 0 and 1 will be half, average of 0 and 1 will be half. So therefore, we will have the corresponding quantity over there. And then the bivariate f of x y, f of x y x comma y is shown in the equation 3.15 for the same. Okay, so that quantity will give us the value which is the what you call f of x y is equal to 1 between 0 to 1 for both x and y. This is what we need to consider, right? And there, if you try to consider it, then at that time the mean values will be equal to each of the value will be 1/2, because they are ranging from 0 to 1. So now EFXY will be equal to from 3.37. 3.37 is already, considered over here by us, right? This is 3.37 xy and this. Okay, so this f of x y x comma y is nothing but 1 between 0 and 1. Okay, 0 and 1, and that's what we have written there. Okay, 0 and 1, 0 and 1, and f of xy is 1. And later we can separate them out, and then we'll get 0 to 1 x dx and integral 0 to 1 y dy. So this will be x squared by 2, this will be y squared by 2, and if you substitute the limit 0 to 1 and 0 to 1, it will become 1 by 4. Also, if you take mu x mu y, we know that it will be half half, and half into half will be 1 by 4. So EFXY and mu x mu y both are same, and therefore covariance of xy is equal to, we know that covariance of xy is equal to E of xy minus mu x mu y. So 1 by 4 minus 1 by 4 will be 0. Also, the correlation coefficient is the covariance xy divided by sigma x sigma y, and because covariance xy is equal to 0, we'll have the rho xy, which is the correlation coefficient, will also be equal to 0. Will be also equal to 0. Now, going for the next problem, we'll now next go for the next case, that is 3.8a. The 3.8a is shown in the figure over here. Okay, 3.8a is a discrete case where at 4 different points, we are taking the probability density function to be equal to 1 by 4, 1 by 4. Okay, 1 by 4, 1 by 4. The value equal to 1 by 4, 1 by 4 at 0, 0, 1, 0, 0, 1, and 1, 1. If you consider this case, then the equation corresponding to that, the probability density function in the discrete case will be equal to this 1 by 4 into del x del y, 1 by 4 del x minus 1 del y, and this we need to substitute in the formula for the expectation of xy. Okay, so expectation of xy will be, we need to substitute xy f of xy dx dy. F of xy, x comma y will be the 1 by 4 into all this. Okay, so now if you integrate this and try to solve this, then we will get this value like this, and then again integration will give us 1 by 4. What is needed to be done is separation of integrals we'll have to do, and then we'll have to do the integration by parts. Okay, separation of integrals we should do, and then integration by parts, we are going to get the final value as 1 by 4. So having got this 1 by 4, again mu x mu y, mu x into mu y will be 1 by 2 into 1 by 2, that is 1 by 4. E of xy is same, equal to the mu x mu y. So again we can say that the covariance, which is E of xy minus mu x mu y, will be equal to 0, and the correlation coefficient, which is covariance xy divided by sigma x sigma y, will also be 0. Will also be 0.